Whoa. Guess no one else is going to show up. Let's get started. So, we finished chapter 5. We just did the lab on chapter 5. The chapter 5 homework is due on the 12th. The chapter 5 quiz will be on the 10th. So next week. So we're starting chapter 6 on waves. So we know that when matter is disturbed, energy emanates from the disturbance. This propagation of energy from the disturbance is known as a wave. You are experiencing energy being distributed via a wave right now, because that's how sound works. And also light. So some examples include ocean waves, sound waves, electromagnetic waves, seismic or earthquake waves. You can send vibrations or waves through various substances. So waves, the general thing about waves is that waves transfer energy, but not material. So when you have a wave, the energy of the wave travels through, but the material itself doesn't move. So like if you have an ocean wave, the ocean mainly just moves up and down, but the energy being transmitted flows along. The wave form is in motion, but not the actual matter. So water waves, the liquid waves, essentially bob you up and down, but they don't really move you sideways. You may have experienced this if you've ever been like a wave pool or something. Earthquake waves move through the earth that is solid. Sound waves travel through the air. So the wave is traveling across the room, but the air coming out of my mouth is probably only going a few inches. And electromagnetic radiation waves travel through space itself. They travel through the void because they're in the fields. Now, a disturbance can be a single pulse or shock, like hitting things with a hammer, or it can be more periodic, like a guitar string or my vocal cords. So you can have a short disturbance or a more periodic disturbance, like and the two types of waves can be classified into two types based on how the particles move with respect to how the wave moves. So the wave is going that way. You could have a longitudinal wave where the particle motion and the wave motion are parallel to each other. So if the wave was going this way, if the particles were going back and forth like this, that would be a longitudinal wave. That's like sound. You can also have a transverse wave where the particle motion is perpendicular to the direction of the wave velocity. So the wave is going that way, but the particles are going up and down or forward and back, but perpendicular to the wave motion. So an example of a light wave is light is an example of a transverse wave. Water waves are more or less transverse. A wave in a string is transverse. So like a guitar string, it moves side to side. The wave is actually moving along the length of the string. So longitudinal wave, like sound, is compression. You have areas of compression and areas of rarefaction where it's stretched out. So you can see that in like a slinky. And then a transverse wave is easiest to see because the wave is perpendicular to the direction of motion. So here is a short video showing the difference between transverse and longitudinal waves.
In a longitudinal...
Oops. I forgot to change the sound back. Here.
In a longitudinal wave, the disturbance that makes up the wave is along the direction in which the wave travels. Longitudinal waves are also referred to as compression waves. In a transverse wave, the disturbance that makes up the wave is perpendicular to the direction in which the wave travels.
Finish. So longitudinal wave, it's along the direction of motion. Transverse, it's perpendicular. So this is a transverse wave. And this is a longitudinal wave. You can see the higher pressure, higher density, lower density, higher density, lower density. And if you look at the pressure, you have a wave that looks like that. When we describe a wave, we describe some of its properties. The distance between two peaks is one wavelength. You can also measure the distance, any two identical points in the wave. So that's the distance for one complete cycle of a wave. So it's from peak to peak, trough to trough, from rising edge to rising edge. The amplitude is the maximum displacement of any part of the wave from its equilibrium position. Basically the height of the wave from equilibrium. And the energy transmitted by the wave is directly proportional to the amplitude squared. So double the amplitude, you quadruple the energy transmitted. We can also talk about frequency. So the frequency of a wave is how many cycles occur during a given time, 1 second. So we usually measure frequency in hertz. So 1 hertz is 1 over a second. They're inverse seconds. 1 hertz is 1 cycle per second. Period is the time it takes for a wave to travel a distance of 1 wavelength. And frequency and period are inversely related. So frequency is 1 over period. And vice versa. Period is 1 over frequency. So if your wave has a frequency of 4 hertz, then 4 full wavelengths will pass in 1 second. And the period will be 1/4 of a second. Because 4 wavelengths pass in 1 second. So for 1 to pass, that takes a quarter second. Period is 1 over frequency, it's 1/4 of a second. And generally we talk about waves with frequencies in hertz or kilohertz or megahertz or something. Like if you listen to the radio, it'll be the frequency of the wave will be listed in kilohertz or megahertz. You might have a Wi-Fi thing in gigahertz. Those are all radio waves. So here we can have a wave with 4 hertz and then 8 hertz. It's half the time. And if they travel at the same speed, it will also have half the wavelength. Because it turns out there's a relationship between frequency, wavelength, and speed. So here we have a long wavelength. Both waves are traveling at the same velocity. This has a long wavelength and a lower frequency. This has a short wavelength and a higher frequency. You can see this is moving back and forth faster. So if a water wave has a period of 0.5 seconds, what is its frequency? I'll give you a moment for consult. So frequency is 1 over period, so 1 over 0.5 seconds, 2 hertz. If sound wave has a frequency of 10 kilohertz, that's 10,000 hertz, what is its period? That's at the high end of human hearing, because human hearing cuts off at around 20 kilohertz. Goes from about 20 to 20 kilohertz. 20 hertz to 20 kilohertz. Unless you're old and beat up your ears like me, and then it cuts off before 20 kilohertz. The frequency is 1 over period. The period is 1 over frequency. 1 over 10 kilohertz is 1 over 10,000 hertz, which is 0.0001 seconds or 0.1 milliseconds. Now, since speed is distance over time, velocity is going to be wavelength over period, because one cycle is one wavelength and one cycle is one period. And that means that velocity ends up equaling wavelength times frequency. The velocity is the speed of the wave, and it's going to equal wavelength times frequency. Wavelength is written with lambda, like you see here. And period of the wave in seconds, frequency is in hertz. So length of the wave times the frequency in hertz gives you a speed in meters per second, because hertz are inverse seconds. So here are two waves with the same frequency but different velocities, and you can see how for a higher velocity, a lower velocity, you have a shorter wavelength, and for a higher velocity, you have a longer wavelength. So if you have sound waves with the speed of 344 meters per second and frequencies of 20 hertz and 20 kilohertz, the two extremes of human hearing, what is the wavelength of each of these sound waves? So given your velocity is 344 meters per second, your frequency is 20 hertz, or 20 kilohertz, which is 20,000 hertz, we want to find wavelength. So velocity equals wavelength times frequency. So if we want to solve for wavelength, wavelength is velocity over frequency, and frequency will be velocity over wavelength. So 344 meters per second divided by 20 hertz is 17 meters. 20 hertz wave at 300 with that's more or less normal airspeed, speed of sound in air. It's a little high, but might be a warm day. And 344 meters per second divided by 20,000 hertz, that's 0.017 meters. So that's 1.77. Now, if a sound wave has a speed of 344 meters per second and a wavelength of half a meter, what is the frequency of the wave? Well, here we'll use that frequency is velocity over wavelength. The frequency is velocity over wavelength, 344 meters per second divided by 0.5 meters per cycle. This is 688 cycles per second, or 688 hertz. So a water wave out at sea has a speed of 50 meters per second and a wavelength of 250 meters. What is the frequency of this wave? Well, this is fairly straightforward. Velocity is frequency times wavelength. Frequency is velocity over wavelength. 50 meters per second divided by 250 meters is a frequency of 0.2 hertz. So that's, one cycle every 5 seconds. Well, if a wave has a wavelength of 2,000 meters and a frequency of 150 kilohertz, what is its speed? That gives you a little while to work on. Well, velocity is wavelength times frequency. So we just need to multiply these numbers together. So 150 kilohertz times 2,000 meters. That's 150,000 hertz times 2,000 meters. That is 300 million meters per second, or 3 times 10 to the 8th meters per second, or the speed of light. This is a light wave. I mean, this is a radio wave, but it's light. At 150 kilohertz, it's down longer than AM radio, but I mean, it's a radio wave. The standard musical note, A above middle C, has a frequency of 440 hertz. And that is literally a standard. Internationally agreed upon standard. There's an ISO number for it. Everybody agreed that we're going to use this number. And it's actually a little higher than it used to be in the past. Big. But it used to vary from place to place, what people use. If the speed of sound is 334 meters per second, what is the wavelength of this note? That's no, that's on a cold day. So velocity is frequency times wavelength. Wavelength is velocity over frequency. 334 meters per second over 440 hertz gives a wavelength of 0.759 meters. So that's the wavelength of that. That's 75, about 76 centimeters. And yeah. Well, we have time, so let's keep going. So let's talk about electromagnetic waves. Right now, you are observing electromagnetic waves. Your eyes detect electromagnetic waves in a slice, small slice of wavelengths. So electromagnetic waves consist of vibrating electric and magnetic fields that oscillate perpendicular to each other and to the direction of wave propagation. So an electromagnetic wave, if it's traveling that way, like the one I am generating from my laser pointer, if the electric field is going up and down, the magnetic field will be going left and right. The field of energy radiates outward at the speed of light, c. The speed of light is the three significant figures. 3.0 times 10 to the 8. Or 1.86 times meters per second. Or 1.86 times 10 to the 5th miles per second. And to a good approximation, this is the speed of light in air. The difference is something like less than 1%. It's like 1,000, if I remember correctly. So here's sort of what you see. As the light travels along the X direction, the electric fields move up and down in the Y direction. The magnetic fields move left and right in the Z direction. And what happens is that the changing electric field creates a magnetic field, and the changing magnetic field creates an electric field. So light is sort of constantly creating itself. And it propagates through the field everywhere. And we can have different wavelengths of light. And many of these have names. They're all the same thing, they're just different wavelengths and energies. Shorter wavelengths, because of quantum mechanical stuff, shorter wavelengths are able to deposit larger energies. Longer wavelengths are lower energies. So at the long wavelength, low energy end, we have like radio waves. AM, shortwave, FM in this range. And longer that nobody uses. But then above the radio waves, we have the microwaves. The microwave has a wave, so this is frequency. Oh, what was the microwave frequency? It's in the gigahertz. Like your microwave. Your common microwave is at 2.45 gigahertz. Thing. Right. Yeah, microwave ovens are at 2.45 gigahertz. And that's because that is like a resonant frequency of water. So it's very good at transferring heat into energy into water. And that has a wavelength of about 12 centimeters, like 12 and a half centimeters. You can actually measure it directly with like a bar of chocolate. Because you can set up a standing wave in your microwave if the waves bounce off the far sides. And you'll get, if you put a bar of chocolate in, you'll get areas that are more melted and less melted. You can measure the wave where you had more melt and less melt.
Is that right? Like so when you put like a plate of food on the microwave, like some areas more hot and like
You can definitely have, well, there's a couple reasons in areas that some are more hot and others are more cold. Certain things absorb microwaves better. You can have standing waves in your microwaves that'll have hot spots and cold spots. That's why it's got that rotating platter. That's to help deal with that. And yeah. And then, well, the microwaves can only penetrate so far through food. So like the outside will be hot, but the inside will be cold. Yeah. That's because the microwaves only go in so far. They get absorbed. But yeah, you can also have just some stuff absorbs microwaves better than other stuffs. So some foods will get hotter than others because they're better at absorbing microwaves. Waters, certain fats and things. So dry things don't heat up very well in the microwave. It's optimized to heat water. But it also works on various fat molecules. So water and fat are the things that it's good at warming up. Then we have infrared. Right now you are emitting infrared light because you have a temperature, and anything with a temperature emits light. And the temperature you are at emits infrared light. And then there's visible light, which is a small segment of wavelengths between, frequencies between 7.5 times 10 to the 14 hertz and 4.3 times 10 to the 14 hertz, and wavelengths between 400 nanometers and 700 nanometers. That's just the range that humans can see with our eyes. And that's centered more or less around the middle of the visible wavelengths is around the brightest portion of the light from the sun. This visible segment corresponds roughly to the middle of what's coming from the sun. Then shorter wavelengths, we have ultraviolet light. And then even shorter, we get X-rays, and then the shortest is gamma. So X-rays and gamma rays, the individual photons, well, individual packets of energy are big enough. So in the ultraviolet, X-rays and gamma rays, they can have energies that are high enough that they can actually damage the molecules, which is why, if they damage DNA, they can cause cancer. So that's how those can give you cancer. And which is why you do not need to worry about getting cancer from 5G, because 5G is down here and the energy is nowhere near enough to mess with anything in your cells. You worry if you get X-rays or gamma rays, but those don't happen very often. You need generally something relatively extreme to generate, or radioactive. And the atmosphere, they come from space, but the atmosphere absorbs them. And then the ultraviolet gets absorbed by the ozone layer. But yeah, skin cancer could be a problem from ultraviolet. So this is the electromagnetic video about the electromagnetic spectrum. Oops. I'm gonna keep pressing the wrong button.
Funny. The man has jokes.
He's funny. Okay.
I forgot to fix this.
Hey, it's Professor Dave. Let's learn about light.
He knows a lot about the science stuff. Professor Dave explains.
Since we've been able to look up at the sun, we've been aware of light. As darkness is one of very few things that we instinctually fear, we have always bestowed light with godlike properties. But for all of antiquity, we had no idea what light really was. Figures like Newton and Huygens worked with light in the 17th century, but a more sophisticated description of light, which we call classical electromagnetism, was developed largely by James Clerk Maxwell in the 19th century. This theory depicts light as a transverse wave composed of oscillating electric and magnetic fields, which are at right angles to each other and perpendicular to the direction that the wave moves. We will learn more about these fields later. Just like the kinds of waves we have previously discussed, electromagnetic waves have amplitudes, wavelengths, and frequencies. But instead of different frequencies producing different pitches, like sound waves, different frequencies of electromagnetic waves produce different kinds of light. If the light is visible, these frequencies will correspond to different colors. Frequencies greater than this will exist as UV radiation, X-rays, or gamma rays, and frequencies less than this qualify as infrared radiation, microwaves, or radio waves. All of these phenomena are collectively referred to as electromagnetic radiation, and they can be found on the electromagnetic spectrum. Here we can see all the wavelengths and frequencies ranging from radio waves to gamma rays, and we have found some technological use for all of these in modern society. Even though they seem dramatically different, some requiring things like antennas or other equipment to manipulate, all of them are fundamentally the same thing as the light you can see with your eyeballs. They are just of different wavelengths. All electromagnetic radiation moves at the speed of light, which is about 300 million meters per second in a vacuum, the fastest speed possible in the universe. This is fast enough to get from here to the moon in about a second. And since we know that all waves move at a speed that is equal to their wavelength times their frequency, this product will be equal to the speed of light for any type of electromagnetic radiation. How is it that electromagnetic radiation is produced? To answer this question, we have to learn about electric fields, which are coming up soon. For now, let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making.
So here's an example of computing the wavelength of a radio wave. If you want the exact speed of light, it's 299.792.458 meters per second. And that's exact. Because we use this fixed value for the speed of light to define our unit of distance. So in the metric system, the speed of light is exact to a whole number. But if you want the wavelength of radio, but for everyday purposes, 3 times 10 to the 8th works. Because that's 3 significant figures, and it's all you'll need for this class. So the wavelength of radio waves produced by a station that's assigned a frequency of 600 kilohertz. Well, first step, convert kilohertz to hertz. That's 600,000 hertz, or 6 times 10 to the 5th hertz. Then we're going to solve for wavelength. Wavelength is velocity over frequency. So that'll be c over frequency. So for light, c equals wavelength times frequency. So the wavelength is going to be 3 times 10 to the 8th meters per second divided by 6 times 10 to the 5th hertz, which will give us 0.5 times 10 to the 3rd meters, or 500 meters. That's an AM radio station at 600 kilohertz that has a wavelength of 500 meters, half a kilometer. And this is why AM radio stations don't get blocked by buildings, because their scale is just so much bigger than the buildings. So AM sits around approximately 800 kilohertz, 8 times 10 to the 5th hertz, while FM is around 90 megahertz, 9 times 10 to the 7 hertz. So AM wavelengths are longer than FM wavelengths. AM wavelengths are in the hundreds of meters, so 3, hundreds of meters, few hundred meters, 800 kilohertz gives you 475 meters, and then 90 megahertz, and 97, that's like 3 meters. So AM radio waves are in the hundreds of meters, while FM radio waves are meters in length. A few meters. So WBEZ broadcasts at a frequency of 91.5 megahertz. What is the wavelength of the WBEZ radio wave? That's our local NPR affiliate. So what wavelength is WBEZ broadcast at? TV is sort of on the high end of the FM. So speed of light is frequency times wavelength. Wavelength is speed of light over frequency. So 3 times 10 to the 8th meters per second divided by 91.5 megahertz is 3 times 10 to the 8th meters per second over 91.5 times 10 to the 6 hertz. Because mega is 10 to the 6. And that comes out to 3.28 meters. Now, visible light waves have frequencies in the range of around 10 to the 14 hertz. So it has relatively short wavelengths. They're nanometers, hundreds of nanometers. The high end, they're a millionth of a meter. They're like 0.4 to 0.7 millionths of a millionth of a meter. These are some rough numbers. And we generally express visible light in nanometers, and the visible light range is from 400 to 700 nanometers. And the human eye perceives different wavelengths within the visible range as different colors, and the brightness depends on the energy of the wave. And so if you have a red LED emitting a light with a wavelength of 660 nanometers, and you want to figure out its frequency, speed of light is frequency over wavelength. Frequency is speed of light over wavelength. So 3 times 10 to the 8th over 660 nanometers is 3 times 10 to the 8th over 660 times 10 to the minus 9 meters. And that comes out to 4.55 times 10 to the 14 hertz. And I will stop there for today. So you are free to go. And I need to make sure when I start sharing, I actually close the meeting.